In the last lesson, we briefly talked about the building blocks of neural networks, which simply consist of taking the linear combination of models to come up with a new model that better classifies the data. First and foremost, this linear model, whose line is represented with the following equation, negative 4x1 minus x2 plus 12, we can represent it with this perceptron. The weights in the input layer, negative 4, negative 1, and 12, represent the equation of the linear model to which inputs are being passed in, to obtain their probability of being in the positive region by multiplying each input with its respective weight, along with the bias value to obtain their linear combination, and then taking their sigmoid. This is nothing new. We've already seen this stuff in perceptron theory. Our second model with the following equation, negative 1/5 x1 minus x2 plus 3, receives the exact same input nodes, which are processed by our linear model by multiplying each input with its respective weights, and adding it up along with the bias to obtain their linear combination, and then taking the sigmoid of the point to obtain the probability. And recall that we combine these two perceptrons, we combine the two linear models to obtain this one, by multiplying the two models with some set of weights and added it to some bias to obtain a new model. In our case, we assigned the first model 1.5 times the weight of the second one, then took its combination along with a bias of 0.5 and applied the sigmoid to obtain the following curve. So it's important to note that in the input layer, the weights indicate the equation of the linear model, and these weights are used to obtain an output, a prediction of the probability of the points being passed in. And in this layer, the weights dictate how the two linear models are combined to form this nonlinear model. To represent this, we'll add another perceptron by first taking the linear combination of our current ones. Don't forget we always consider a bias of 1, where the first linear model, the first perceptron, is multiplied by a weight 1.5, and the second perceptron is multiplied by a weight of 1, taking their combination along with a bias of 0.5, and then applying the sigmoid to obtain the curve. All we're doing is taking the combination of our models and applying the sigmoid to then obtain a nonlinear model which better classifies our data. Going back to our previous example, suppose we had two inputs, x1 and x2, which represent a single point at coordinates 2 and 2. And we wanted to obtain the probability of the point being in the positive region in the nonlinear model, the model which best classifies our data. These two inputs, the point at coordinates 2 and 2, is passed into the first layer, which consists of two linear models. The two inputs are processed in the first linear model to obtain the probability of the point being in the positive region by taking the inputs as linear combination based on the weights and bias of the model, and then taking the sigmoid. We obtain a probability of 0.88. It is therefore 88% likely that the point is in the positive region of this model. We also obtain the probability of the point being in the positive region of the second linear model, which ultimately results in a value of 0.64. In the first model, this point is assigned a probability of 0.88, and in the second one, a probability of 0.64. When we're superimposing both models, we're adding them together. We're taking their linear combination with respect to weights of 1.5, 1, and a bias of 0.5. Thus, we must do the same thing for our point in the first and second model. We multiply the point in the first model with the first weight 1.5, and the point in the second model with the second weight of 1, adding everything up along with the bias to obtain the score. And since we're taking the sigmoid of the linear combination of both our models to obtain a new model, we must do the same thing for our points, which ultimately converts it to a 0.92 probability of it being in the positive region in the nonlinear model. What you just saw is known as the feed-forward process of a deep neural network. If you're confused by it, we'll cover it in a lot more depth later on. For concision, we can rearrange the notation of this neural network. Instead of representing our point as two distinct x1 and x2 input nodes, where each one goes into a separate model, we can represent it as a single pair of x1 and x2 input nodes. That is, instead of having two of the same x1s, we'll have a single x1 that's multiplied by the weight of the first linear model and multiplied by the weight of the second linear model. We'll also have a single x2 that's multiplied by the weight of the first model and the weight of the second, and the same goes for the bias. It's multiplied by the bias value of the first model and the bias value of the second, and this is really the exact same thing as what we had previously. Nothing changed, since the same concept applies, as we're still taking the linear combination and sigmoid of our point in the first model to obtain a probability of 0.88, we're still taking the linear combination and sigmoid of our point in the second model to obtain a probability of 0.64, and doing it again with respect to weights of 1.5, 1, and 0.5 to ultimately obtain the probability of the point being in the positive region in our optimized nonlinear model in the final layer. This demonstrates the unique architecture of a neural network. The first layer is called the input layer, which contains the inputs x1 and x2, but now, unlike our single perceptron-based model that we saw in the last section, instead of processing these inputs directly in the output layer, first they must go through the hidden layer, which is simply a set of linear models, and the final layer is the output layer, which resulted from the combination of our two linear models to obtain a nonlinear model. The more hidden layers we have, the deeper our neural network gets. Hence the term deep neural network. We're simply using the models in the hidden layers to combine them and create nonlinear models which best classify our data. Sometimes our data is so complex that we'll have to even combine nonlinear models to create even more nonlinear models. We can do this many times with even more hidden layers and obtain highly complex models, like the one you're seeing right now. Data this complex requires many hidden layers of models combining into one another with some set of weights to eventually obtain a model that perfectly classifies this data. From that model, we can then produce some kind of output through a feed-forward operation, although the inputs would have to go through the entire depth of the neural network before an output is produced. If you really think about it, really all of this is just a multi-layered perceptron. If we go back to the perceptron from our diabetes example, we used gradient descent to eventually obtain the perfect linear model to predict whether someone was likely to be diabetic or not. However, in order to obtain this model, there were no hidden layers, simply one input layer and one output layer. The reason why we don't need any hidden layers is because this data's trend is very straightforward. A linear model is enough to perfectly classify it. The same concept applies here with deep neural networks, except in deep neural networks, our data's trend is not straightforward. As you can see here, it's very complex. And so this nonlinear boundary is just an accurate model that correctly classifies a very complex set of data. However, to obtain this nonlinear boundary, we need many hidden layers, each layer containing models that combine into one another to produce this very complex boundary that classifies our data. The more layers you have, the deeper the neural network, and deeper neural networks can be trained to learn even more complex functions, to classify even more complex data. To conclude this lesson, let's have a more general representation of our neural network, such that x1 is multiplied by w11, so as to indicate the first weight in the first linear model, and it's also multiplied by w12, indicating the first weight in the second linear model. And accordingly, x2 is multiplied by w21, the second weight of the first model, and w22, the second weight and the second model. And the bias is denoted as 3, it's multiplied by w31, the bias value in the first model, and w32, the bias value in the second model. For every weight and bias value, we'll add a superscript 1, so as to indicate the first input layer. We'll do the exact same thing for the hidden layer, except now the superscript is 2, since this is the second layer, which eventually leads to the output layer. That is really it for the architecture of deep neural networks. All we're doing is simply combining models to obtain more complex nonlinear models that best classify complex data.